Alright, now we continue with our discussion of very special graphs. We are dealing with constant acceleration problems for which the kinematic equations are valid, and we've just found that from the velocity time graph we get this equation for position, known as the second kinematic equation. It says the final location of an object is equal to 1/2 times the acceleration, which is a constant, times the time squared, plus the initial velocity of the object times time, plus the initial position. If you drop an object so that the initial velocity was 0, this term would go away. If you start the object at the origin, this term would go away. If the object had no acceleration, this term would go away. Now, this is a parabola as shown in the position time graph. The point at which it crosses t equals 0 is x naught. This is this constant right here. In general, in math class, you write parabolas this way. A/t squared plus bt plus c. And in fact, in Logger Pro and other software, but we're using Logger Pro, we can use its modeling capability to model parabolas with these three coefficients being found, a, b, and c. I want to look at those three coefficients for a second. This coefficient a corresponds to 1/2 times the acceleration of the object. So if you find a, then if you multiply it by 2, you can get the acceleration of the object. An example of that would be free fall. In free fall, this a would be 4.9, and when you multiply by 2, you would get the acceleration of 9.8 meters per second squared. Notice also the units have to be right. The units of this, when multiplied by second squared, has to give you meters. So this coefficient has the units of meters per second squared. This combination, b times t, has to give you the units, again, of x, which are meters, so b has to have the units of meters per second, which are the units of a velocity. And in fact, what it is the initial velocity. So again, by fitting in Logger Pro a parabola, this b would give us the velocity when t is equal to 0. Now, if you start fitting something at a later time in Logger Pro, then you're going to have a problem. You need to have t minus t naught, whatever the initial time is. So you'll need to create a new column in order to set your new time. This happens sometimes in the videos when you're holding the object and you don't let it go when the video starts. Likewise, this c is x naught, the initial position of the object. So by fitting a parabola of this and getting these three coefficients and knowing about what this graph has to tell us, we can find x naught, v naught, and 1/2 a. Another important thing to make sure that you put in your memory is parabola on a position time graph means that object is undergoing constant acceleration. Alright? And it's a constant acceleration, I might add, that's not 0. Alright? If it's a straight line, it's got a problem which is constant acceleration, but the acceleration is 0. This is a question when people ask you, is the kinematic equations valid, or can we treat this as constant acceleration? The question, if you're looking at a position time graph, is it a parabola? If it's a parabola, then it's got acceleration that's constant. If it's a straight line, it's acceleration of 0. If it's not either one of those, then the answer is no. The acceleration is not constant, it's variable. It's changing. Alright? That covers this section. We're now going to look at the third kinematic equation, which also comes from the velocity time graph. If you have a straight line on a velocity time graph, then you have a constant acceleration problem and the kinematic equations are true. Notice, in order for them to, you must always a straight line on a VT graph if constant acceleration. If you don't have that graph, then you cannot use the kinematic equations. What we're going to do is we need to find a formula for the average acceleration. Now the average acceleration is always, without exception, always the change in x over the change in time. And for our problem, since we're going to start the initial time at 0, that's simply delta x over t, because we're subtracting 0 from t to find the change in time. So in our particular problem with this graph, at some time t equals 0, you initially have a velocity of v naught. At some later time t, you have a velocity of v, and I wish to find your average velocity over that time interval. I could find the area under the curve to find delta x and then divide by t, and that would work. However, there's another way to do it if you have a straight line. If you have a straight line, what you can do is you can take the final value of your velocity, add it to your initial velocity, and divide by 2. So v average is equal to v plus v naught over 2. Special case only true for straight line. So let me show you that that's actually true. I'm going to come up here and take the midpoint here. It's about 3 seconds. Draw my line up here where it hits the graph, and then pull that over here. I almost got it right, at least close. Not quite right, a little low here. But my point is that there's where the average is. Halfway between V naught and V, because this graph went up straight with a constant acceleration. Had it been any other type of graph, it wouldn't work. Let me give you an example of that. Let's assume that over a 5-day period, you're going to add $1,000 to a bank account every day. So day 1 you had 1,000, day 2 you had 1,000, day 3 you had 1,000, day 4 you had 1,000, day 5 you had 1,000. So $5,000. Your average input is $1,000 a day. 5,000 divided by 5. Let's now do it where you did it for 5 days, but on the last day, the 5th day, you didn't put anything in. Well, in that case, you did 4 times you put in 1,000. So you have $4,000 in the bank. The 5th day, you didn't put anything in. Over those 5 days, you'd find the average is 4,000 divided by 5. Or it's equivalent to putting in $800 every day 5 times. 800 the first day, 800 the second, 800 the third, 800 the fourth, 800 the fifth, and at the end of the time you'd have the same amount of money, $4,000. So you can see that the amount of money wasn't halfway between the most we put in, 1,000, and the least, 0, because the half would have been 500. It is closer to the $1,000 because we did that more times. So if you had had a graph where you put in 0, 0, 0, 0, and then the last day put in 1,000, then your average would have been 1,000 divided by 5, or 200. It had been closer down to 0 because that's the one you put in more often. It wouldn't have been 500. Only a graph like this, where it's 50% of the time above and 50% of the time below, a straight line graph, does this formula here work. This formula is always true and requires to find the area in the curve. This formula only works for straight lines, but we have a straight line. And so we can use that straight line to go and help us derive a really nice formula for getting rid of time out of one of the kinematic equations. Okay, I've written down the 2 facts that we know, that the Average velocity is the change in position over time. Remember, it's t minus 0, so I don't need the delta. It's t and delta t are the same. And I put in what x is, x minus x naught, and this fact that we know for straight lines that the average is v plus v naught over t. And now I want to solve these two equations. I want to solve this for t. So from the top equation, I have t is x minus x naught over v average. And if I plug this equation in for v average, I get 2 times x minus x naught. And on the bottom, v plus v naught. So this is an equation for time of an object. If you told me v, v naught, x, and x naught, I could tell you what time that it was that the object was at that location with those speeds. Now what I want to do is I want to go and plug that back into one of our previous equations. Remember that delta v, which is v minus v naught, is equal to a times t, assuming constant acceleration. This was because we had that rectangle for constant acceleration problems. So I can now plug in for t using my formula above here. And I have v minus v naught is equal to a times 2 times x minus x naught over v plus v naught. I'm going to take that denominator and bring it out front. V minus v naught, v plus v naught, bring in this one, times that. V minus v naught is 2 times a times x minus x naught. Well, this is something we should know from algebra. This is a plus b, and this is a minus b. And this is called the difference of the perfect squares. So when you multiply something like that, you get a squared. What's a? Well, a is b. V squared minus b squared. What's b? That's v naught. Is 2a x minus x naught. Or it's usually written as v squared is v naught squared plus 2 times a x minus x naught. This is the third kinematic equation. Again, only true for constant acceleration problems.